Hello, welcome to section 1.5 of the M132 course Introduction to Linear Algebra at AOU. In this section we will talk about matrix equations. In other words, how we can transform, how we can write a system of equations, system of linear equations into a matrix equation and solve the system accordingly. Let's start off with a few definitions. Number one, if AX equal to B, where A is the coefficient matrix, X is the variable matrix, and B is the component matrix. If this is a linear system of n equations and n unknowns, and if A is non-singular, that means A has an inverse, invertible, then the linear system has a unique solution obtained by X is equal to A minus 1 times B. In other words, X is the product of the inverse of A times B, which is the component matrix. This is definition 1, for which we will have a few applications and examples later on. Definition 2, if A is an n by n matrix, singular matrix, A being the coefficient matrix. Singular means non-invertible, does not have an inverse. Then the linear system AX equal to 0, which we call a homogeneous system, has a non-trivial solution. Non-trivial meaning infinitely many solutions. So then, if we repeat, if A is a singular matrix, then the system AX equal to 0 has a non-trivial solution, meaning infinitely many solutions. On the other hand, if A is a non-singular, meaning has an inverse, then AX equal to 0 has the trivial solution X equal to 0, meaning all the variables will have a value of 0. Below we will look at some examples related to the above two definitions. Example 1, if A is a 3 by 3 matrix as shown here, and B is the component matrix that we have here, column matrix, and we need to solve the system AX equal to B. Again, solving the system means finding the matrix X, the components or the elements of the matrix X which satisfies this equation. As seen above, the solution is X equal to A minus 1 times B. How we obtain this is as follows. We multiply both sides of the equation by the inverse of A from the left hand side, as seen here. A minus 1 times AX is equal to A minus 1 times B. But A minus 1 times A is the identity matrix. Therefore, X is equal to A minus 1 times B. And A minus 1 we have found before in a previous example that we have done in the section 1.4. If we multiply these two matrices together, we obtain the matrix of the coefficient of the variable, the variable X. Therefore, X1 is equal to 1, X2 is equal to minus 1, and X3 is equal to 2. Okay. Example 2, if A is equal to a 3 by 3 matrix, again is a coefficient matrix that has 3 by 3 elements as shown here. The questions are, part I, is A non-singular matrix? Explain. We have to prove that A is singular or non-singular, and we have to show how and why. Part 2, solve the linear system AX equal to 0 based on the findings in part I. As we know, to determine if A is singular or non-singular, we have to find out if A has an inverse. How we do this is we expand the coefficient matrix by the identity. We obtain the augmented matrix, which is a 3 by 6 matrix. And as we've done before in section 1.4, we run the row reduction on the matrix as we see here, using the row operations stated here to obtain this matrix here. As you can see here, this matrix here is it has on this side, on the left side, it has a row of zeros, and as we have seen before, When we obtain a row of zeros, it means that the matrix is not invertible. The matrix is not invertible, that therefore A is singular. Now, since A is singular, we can move to address question part 2 of the problem. So then, as we have seen in the definition, if A is singular, the system, the homogeneous system AX equal to 0 has infinitely many solutions obtained from the reduced row echelon form. So we take the equivalent matrix here, this is equivalent to the original one, and we set it equal to 0. Therefore the solution set is S is equal to minus 3t, t and t where t belongs to R. Therefore x is equal to minus 3t, y is equal to t, and z is equal to t. Example number 3. If A is equal to a 3 by 3 matrix as shown here, and B is a 3 by 2 matrix, we need to find A2 minus 1. We also need to find the matrix X such that A transpose times X equal to B. And part triple I, we need to find the matrix Y such that Y times A is equal to B transpose. Let's first try to find A2 minus 1. To do that, we find the inverse of A first. Inverse of A is as such. You can verify this by doing it yourself. So the inverse of A minus 1 is this. What we do then is, in order to address the question, A to the power 2 minus 1 is equal to A minus 1 to the power 2. We take the inverse of A and raise it to the power 2. In order to do that, we set the two matrices next to each other and we do the matrix multiplication as we've learned before. If we do that, we obtain this matrix here, which is again a 3 by 3 matrix. This matrix here represents A to the power 2 minus 1. Now, to address part 2 or part double I of the question, A transpose times X equal to B, we need to find the value of X that satisfies this equation. To do that, we need to isolate the X. To isolate the X, we multiply both sides of the equation by A transpose to the minus 1, or the inverse of the A transpose matrix. We multiply both sides of the equation from the left hand side, this one from the left and this one from the left. But the multiplying these two produces the identity matrix. The identity times X means X is equal to A minus 1 transpose times B. If we set the matrices as defined here, we have this is A minus 1 transposed times B that we have from before. We do the multiplication. This is a 3 by 3 matrix and this is a 3 by 2 matrix. The multiplication can be done to produce a 3 by 2 matrix as seen here. For question part triple I, YA equal to B transpose, we need to find the value or the elements of the matrix Y that satisfies this equation. For this reason, we multiply both sides of this equation here by A minus 1 from the right hand side to obtain YA A minus 1 equal to B transpose times A minus 1. Therefore Y is equal to B transpose times A minus 1. We take the value of B, the matrix B, we transpose it, we multiply it times A minus 1, which we have from the beginning of the exercise. We do the multiplication. This is a 2 by 3 and this is 3 by 3 to obtain a 2 by 3 matrix as such.